So let's get started. Today we're going to be talking about indefinite integrals, definite integrals, the U substitution, fundamental theorem of calculus, properties of integrals, exponential functions, and logarithmic functions. So that was a lot, and we're going to get started with the most basic stuff, indefinite integrals. Indefinite integrals. So let's get started with indefinite integrals. Number one, I just want to know what is the integral of the square root of 2 dx. An easy one to get started. So I've got good news for you. This is a very easy integral. It follows the constant rule, which pretty much says if I have the square root of 2, and it doesn't matter what the number is, like the number could be 2, the number could be 5, the number could be 12, could be negative 1/5. It doesn't matter. Whenever you have an integral like this, I'll just write all of these real quick because all of them take 2 seconds to do. The integral of square root of 2 dx is going to be square root of 2 times x plus c, final answer. In other words, if you don't see an x in the integral, literally just add an x and you're done. So just to go down this list of 4 right here, integral of 2 dx is 2x plus c. Integral of 5 is 5x plus c. Integral of 12 is, you guessed it, 12x plus c. And then the last one, integral of negative 1/5 would be negative 1/5 x plus c. I'll give you like 10 seconds to write this down, but it's very easy whenever you just have a number and an integral. It's literally you just add x. Hopefully some of you remember that. Okay, we're going to move on to number 2 now. Number 2, we're going to ramp up the difficulty substantially. We have the integral of 7x to the 4th plus x to the 1/2 minus 2/3 x to the 3/4 power end parenthesis dx. This just looks terrible. I know. I apologize. But here's what I'm going to tell you. It follows the power rule for antiderivatives. What does that mean? So just a quick recap. If we were talking about derivatives and I had like x to the 4th, well, the derivative of x to the 4th, you pull the 4 out in front, right? And then we say minus 1 power, so it would become 4x cubed. We're going to do the opposite of this for the power rule for antiderivatives. Instead of saying minus 1, I'm going to say plus 1. So look at this first one here, 7x to the 4th. Another thing worth mentioning, just real quick, whenever you have an integral like this with like the plus signs and the minus signs separating thing, this is not a U substitution because everything is just plus or minus. This is actually a pretty straightforward example despite how crazy it looks. What I'm trying to say here is I can break this up into 3 separate integrals. It's the integral of 7x to the 4th dx plus the integral of x to the 1/2 dx minus 2/3, I missed the integral, minus integral of 2/3 x to the 3/4 dx. We can split it up into 3 different integrals. This is obviously helpful because now it's very straightforward what each integral is. It's going to be 3 power rules for antiderivatives, and here's how we do it. So first, 7x to the 4th power, I'm going to rewrite that as 7 integral x to the 4th dx. The reason I did that is because the 7 is a coefficient, which means I can just write it out in front. And the integral of x to the 4th, this is where the power rule kicks in. Integral of x to the 4th is going to be x to the 4 plus 1 power, so 5, divided by that power, 5. This is the integral, 7x to the 5th over 5. We're about to do a bunch of these today, so get used to the power rule if you don't remember it. Okay, that's it for the first one. Now the second one, integral of x to the 1/2 dx. Once again, I need to add 1. This is not fun because a lot of you suck at fractions for some reason. I blame your middle school teachers, but that's besides the point. X to the 1/2 plus 1 power. Well, 1/2 plus 1 is the same thing as 1/2 plus 2 halves. Get a common denominator. That's a horrible 2. Okay, 1/2 plus 2 halves. That would be then x to the 3/2 power. 1/2 plus 1 is 3 halves. X to the 3/2 divided by 3/2. We'll simplify that in the next step. But that's it for the middle term. I'm going to clear some space here. And now we need to focus on the last one. Minus 2/3 x to the 3/4. Again, this 2/3 is a coefficient. I can write that out in front like this. Times x to the 3/4. Need to add 1 to that. What is 3/4 plus 1? So instead of plus 1, I'm going to write plus 4 fourths, get the common denominator again because that's helpful. That's going to be 7 fourths, which means this integral is x to the 7 fourths power divided by 7 fourths. Again, I'm going to simplify that in the next step. And now that we've finished all three integrals, now I'm going to put plus c, because you cannot forget the plus c after your integral. Hopefully all of this is starting to ring a bell. Okay, so this is a good second to last thing I'm going to write. The last thing I'm going to write is, well, the more simplified version of this. And that is, I don't like complex fractions. I'm going to change it all the time. What is a complex fraction? It's this 3/2 in the denominator and this 7 fourths in the denominator. Everything else is pretty much fine. So I'm going to rewrite this as, the first term stays the same. I'll even write it as 7 fifths x to the 5th power. That's fine. Plus, here's where it gets annoying. X to the 3/2 divided by 3/2. The way we deal with complex fractions is I take the reciprocal of my denominator. What is the reciprocal of 3/2? It's 2/3. So 2/3 times x to the 3/2. That's how I rewrite it. Now it's a normal fraction. Before it was a fraction in the denominator. The way we changed it, again, we took the reciprocal. Any questions so far? Don't be afraid to ask. So now, minus 2/3, because that's the third term now. And the 7 fourths into the denominator, I'm going to rewrite as, I'm going to flip it. So now it's 4 sevenths as a normal fraction times x to the 7 fourths plus c. You could even combine the 2/3 and the 4 sevenths if you wanted to. I'll just leave it like this. This is fine. And this is going to be our final answer for this one. Any questions? Again, the biggest part about this one is just knowing how to do the power rule for antiderivatives. Obviously, it's going to take a lot of practice. We're going to be looking at a lot more of these types of questions today. So stay tuned. And honestly, I'm done with my indefinite integral questions. That's it for indefinite integrals. Obviously, you have more practice to do on your own. But I want to move on to U substitution because, well, it's still going to be indefinite integrals, but now it's substantially harder because U substitution is harder. Now, the first thing I want to talk about is, when do we need a U substitution? Let's talk about that with our first problem here. Number 1 for U substitution. I have the integral of quantity x plus 1 times the quantity 2x squared plus 4x minus 4. That's raised to the 5th power dx. I'll give you a second to write this down. So now, how do I know this is a U substitution problem? First of all, U substitution comes into play whenever we have product rule, quotient rule, or chain rule in an integral. Why is that? Well, because we don't have product rule, quotient rule, or chain rule with integrals. Instead, all three of those cases get replaced with the U substitution. So here's what I'm going to do for the U substitution. I know we talked about this last week or 2 weeks ago. I know most of you forgot about it, so I have to repeat myself, which is fine. The first thing I need to do is pick my U. My U is going to be, I'm going to follow the Goldilocks Principle, which is a made-up thing I talk about, which pretty much says I choose the U to be the thing in the middle. I don't choose the thing that's too short, which would be x plus 1. I don't choose the thing that's too long, which would be 2x squared plus 4x minus 4, all raised to the 5th power. I'm going to choose the thing that's just right. It's the thing in the middle. This 2x squared plus 4x minus 4. This is the right U for the U substitution. And we'll talk about how you can check if you use the right U for the U substitution, because a lot of times this feels like a guess. A lot of times this is like a guess and a check, and you can be going down one very wrong road for like 5 minutes, and then you realize, oh, I did this wrong. That's going to come with practice. You're going to get better and better at choosing your U's for the U substitution, but for now, I would just recommend trying to use this thing in the middle principle, this Goldilocks principle that I made up. So after you choose your U, the next thing we need to do is, even though this is an integral problem, we need to find the derivative of our U. In other words, we need to find du dx. It's also known as U prime. I do not write U prime though, because I ultimately need to solve for dx, so I can plug it back into my integral at the end there. See that dx at the end of the integral? That's why I need the d to solve for dx. So now let's take this derivative. The derivative of 2x squared plus 4x minus 4. Hopefully, all of you are good at this. It's going to be 4x plus 4 minus 0. This is it. Now again, I need to solve for dx. So how do I do that? I'm going to multiply both sides by dx. So on the left, I have du. On the right, I now have 4x plus 4, that quantity times dx. And now all I need to do to solve for dx is divide both sides by 4x plus 4. So du divided by 4x plus 4 is equal to dx. Now I have my dx. I can plug it in right there. And I'm also going to plug in my u for the u substitution. This is starting to get cluttered. Let me rewrite this. I have the integral of quantity x plus 1 times the 2x squared plus 4x minus 4 got replaced with u to the 5th. And then dx we just said got replaced with du divided by 4x plus 4. Now, at this point, I'm going to give you a second to write this down. At this point, how do we know we chose the right u for the u substitution? We know we chose the right thing if all of our x's cancel. There's no x's left over at the end. I see two x's right here, this one right here, this one right here. To me, it does not look like they easily cancel out. However, it does not mean we start over quite just yet, because it looks like it almost cancels out, doesn't it? And that's because, well, it almost does. The only thing we're missing is we need to factor our denominator right here with the 4x plus 4. I'm going to factor out the common term, which is a 4. What I have left in parentheses now is just x plus 1. And when I write that, now you see that this x plus 1 in the denominator cancels with that x plus 1 in the numerator. And what I really have here is the integral of u to the 5th times du, still divided by 4 though. We didn't get rid of that 4. Any questions so far? I know I wrote a lot before asking questions. Okay, assuming you're all good. The next thing I need to do is I need to take this integral of u. A lot of you out there at this step will plug back in for u. Like you'll say, oh, well, the integral of, what was it? 2x squared plus 4x minus 4. 2x squared plus 4x minus 4. Don't write this, by the way. This is horribly wrong. But you'll say this. You'll say du over 4. And you'll say, okay, what's this integral? Here's the problem. This integral is even worse than u to the 5th times du over 4. In other words, the whole reason we did the u substitution was so that it was easy to take the integral. If you plug in for x before we take the integral, it completely undoes any work we just did. Don't do that. I see all of you do it, so I'm telling you not to do it. Well, pretty much, I made the mistake for you so that you will not make it on your own. You probably will make the mistake anyway, but I try. I try to help you guys. So it's the integral of u to the 5th times du over 4 still. Here's what I'm going to tell you to do. This integral would be easy if it weren't for this 4 in the denominator here. This 4 is a coefficient, which means I can write it outside of my integral as 1/4. Why did I write 1/4 and not 4? Well, because this 4 is in the denominator, so it's 1/4. I see a lot of mistakes with that too. Then the integral of u to the 5th du, and hopefully we all know this integral because it follows a simple power rule. I need to add 1 to the exponent, so still the 1/4 out in front, times u to the 6th power divided by 6, close parenthesis, and then we can't forget plus c. Now we're not done the problem yet. Not just because we can simplify the 4 and the 6. I don't care about that. What we do need to do, though, is plug in for u. This is when we plug in for u. It's the last step. You need to do it. So, I mean, I can write 1/24. It doesn't matter. The 4 times the 6 in the denominator gives me 1/24 times u, we said was 2x squared plus 4x minus 4. So quantity 2x squared plus 4x minus 4. That is raised to the 6th power plus c. This is my final answer. Any questions?
You don't raise to the 5th power anymore. You keep the 6th there.
I'm sorry, can you repeat that?
How come you raise it to the 6th power and you don't raise it to the 5th power?
That's because back in when
Or
we
was
had
it always a 5?
What'd you say?
No, I thought I wrote the problem. No, never mind.
You're good?
Same question. Yeah.
Okay. It's u to the 5th before we take the integral. And then when we take the integral, the power rule says we add 1 to the power. That's where the 6 is coming from.
Okay, so always use the integral when you plug it back in.
I'm confused by that question. Do you understand where do I lose you? Do I lose you at this step, or the final step?
No, never mind. I'm good.
You're good?
Yeah.
Okay. Just in case anyone else is confused, because I see a lot of people confused in many of my lessons, so I'll just quick mention it. Pretty much what we're saying here is we have, like, let's say x squared dx, and we need to do the antiderivative for power rules, which pretty much means I add 1 to the exponent, x cubed over 3 plus, that's supposed to be a c. If I have, let's say, integral of u to the 5th du, which is what we just had in this one, then it would be u to the 6 over 6 plus c. Whatever the variable is, u, x, w, whatever, you add 1 to the power, divide by the exponent. And it gets annoying, again, whenever you have a fraction, like integral of x to the 1/2 dx, let's say, because then you need to add 1 to 1/2, which is never fun, but that's just 3/2. So in this hypothetical scenario, you would have x to the 3/2 divided by 3/2 plus c. And again, I don't like complex fractions. I don't know if you'll lose points for it on the quiz, but if I were a professor, I would take points off, and I've seen other professors take points off, so I don't chance it with you guys. So the 3/2 can be rewritten as 2/3 as a normal fraction times x to the 3/2 plus c. This is what we're saying with the power rule. Okay, I'm going to move on. If you have any more questions, talk to me after the review. Sound good? So that's it for the first one here. Number 2 for U substitution, we have the integral of, in the numerator, 3x. In the denominator, I have the square root of x squared plus 1 dx. Okay. So once again, we're going to need to do a U substitution. I'm also going to save us a step right now and just say, yes, we can write the denominator as numerator 3x, denominator quantity x squared plus 1 to the 1/2 power. Yes, that's a good idea. We are going to be doing that at some point. So now, again, this is U substitution. Why? 2 reasons. 1, this looks like a quotient rule. 2, this also looks like a chain rule. And 3, we don't have quotient rule, chain rule, or product rule in integrals. Instead, we do U substitutions. So I need to choose my U for the U substitution. I'm going to give you like 10 seconds for each of you individually. Don't say it out loud. I don't care. Just think in your head what the U is going to be in this U substitution. If you know it, great. If you don't, I'll tell you in 10 seconds. Okay, that's enough time. The U is going to be just x squared plus 1. If you got it, great. Give yourself a pat on the back. If you got it wrong, whatever. It doesn't matter. As long as you know what to do before the test day, I suppose. That's all that matters. So after we find our U, we then say du dx, again, the derivative. In this case, the derivative of x squared plus 1 is 2x. And then, again, we need to solve for dx. So du is going to equal 2x times dx. I multiply dx on both sides. And then divide by 2x. So du divided by 2x is equal to dx. And now I'm going to plug in for dx here. Right there. And I'm also going to plug in for u in the denominator. So this is going to equal the integral of, the 3x does not get touched. We are not replacing that. X squared plus 1 in the denominator does get replaced with u, now to the 1/2 power. And then we said dx is equal to du divided by 2x. Okay, good so far. Now question, do we have x's left over? The answer is yes. And follow-up question, do the x's cancel out? Also yes, which is fine. It means that we chose the right u for our U substitution. Again, if we were wrong, then we would have like an extra x left over somewhere, or something really complicated or convoluted. But since all the x's canceled out, we know we chose the right u. And even if we did choose the wrong u, it's not the end of the world. We just start the problem over, and hopefully you have a good enough eraser. So now let's simplify this. This would be an easy integral if it weren't for 2 things. Number 1, this 3 and this 2 coefficient is kind of annoying us. And number 2, u to the 1/2 in the denominator is also a pain. I'm going to deal with the numbers first, the coefficients, the 3 and the 2. Again, they are coefficients, which means I can pull them out in front. 3 in the numerator, 2 in the denominator, integral of 1 over u to the 1/2 power du. Okay? The 3 and the 2 are just coefficients. I can write it out in front of the integral, and the 2 is in the denominator. Another thing I just want to mention real quick, some of you like to write this as du divided by u to the 1/2. Like you'll put the du here instead of to the right of it. I hate this personally. I think it's confusing. I will always write it as du to the side like this, not on top. If you don't know what I'm talking about, it's not that big a deal. Just keep going. So the next thing I'm going to say is u to the 1/2 is also annoying because, well, it's in the denominator. I'd like it to be in the numerator, but how do I move exponents or powers from the denominator back to the numerator? And the way I do that is by saying this is equal to 3/2 times the integral of u to the negative 1/2 power. Remember that? We did this for integrals too. I mean derivatives. We did this for derivatives too. So u to the negative 1/2 power times du. Now this follows a not so simple but still possible power rule for antiderivatives. In other words, I'm going to add 1 to the power. Negative 1/2 plus 1 is now positive 1/2. So it's 3/2 times u to the positive 1/2 power divided by 1/2 plus c. You already know what I'm going to do, or at least hopefully you do. This 1/2 in the denominator I'm going to rewrite as 3/2 times 2 over 1. Again, complex fractions can be rewritten by just taking the reciprocal. And then instead of u to the 1/2, I'm going to say, what was my u again? U was x squared plus 1. So now it's x squared plus 1 to the 1/2 power plus c. We see these 2's are going to cancel. I'll get a final answer of 3 quantity x squared plus 1 to the 1/2 power plus c. And if you wanted to, you could also write x squared plus 1 to the 1/2 power as a square root. That would be correct as well. It doesn't matter. Both of these are correct. Any questions?
Where did the u go? Like when it went from
u to the 1/2 to the x squared plus 1 to the 1/2? Like,
yeah.
Like right here to right here? Yeah, so that just
and like how'd you get the 2 over 1 also?
Sure. So the u, first of all, the u was just a simple, like, I plugged back in for u. U was x squared plus 1, right?
Yeah.
That's what I did, and I have to do that. I can't leave it as u.
Okay.
Now the 1/2 is a little bit trickier because this is, do you know what a complex fraction is? If you don't know what it is, it's this. It's like a fraction within a fraction.
Okay.
And the way we get rid of that, because, again, sometimes you'll lose points for notation depending on your professor. The way you get rid of that is you need to take the reciprocal of this. What's the reciprocal of 1/2?
Oh, okay. 2 over 1.
Yep, and that's where it came from.
Okay, thank you.
Yep, no problem. Any other questions? Okay. So that's it for U substitution. If you have any questions, just let me know. But now we're going to move on to the next topic, which is exponential integrals, or really just integrals with exponents in them. These problems are, in my opinion, kind of fun compared to the other ones. In my opinion, they're actually too easy. I don't like them. But for you guys, they'll probably be harder because they look funny. But that's okay. I'm here. I'll hold your hand. So the first thing I'm going to tell you is we're going to look at this first problem here. The integral of e to the x dx. Some of you might know this. Some of you might not know this. If you've met with me already this week, hopefully you know this. But this integral, if you don't know it, I want you to first think about the derivative of e to the x. If I asked you what's the derivative of e to the x, hopefully you'd tell me it's e to the x. It's the derivative of itself. It's the only function in the world that does that. And you would be correct. Now, if the derivative is e to the x, then shouldn't the integral also be e to the x? And that would be correct. The integral is e to the x plus c. And that's going to happen. It needs to be e to the x in order to be itself. If you have e to the x, the integral is e to the x. And the reason that's important, and I really want to make this point, is because if I have the integral of, let's say, e to the u du, well, then this integral is equal to e to the u plus c. Now you're starting to think, hopefully, U substitutions and exponential integrals. And some of you hate this, and others of you are getting excited inside. And then there's a third group of you who really don't know what's going on, and that's okay. You are in for a rude awakening over the next two problems. So here's problem number 2. I have the integral of e to the 7x minus 1 dx. What is this integral? So first of all, I cannot just say it's e to the 7x minus 1 plus c. This is wrong. You cannot do this. This is not right. Instead, what we need to do is we need to do a U substitution. And whenever you have e to whatever power, most of the time, the u is going to be that power. In other words, u is equal to 7x minus 1. This is the right u for this problem. Then, as usual, I'm going to say du dx, the derivative, is equal to just 7. I'm going to multiply both sides by dx. So du is equal to 7 dx. And then I divide both sides by 7 to solve for dx. So du over 7 is equal to dx. I can plug that in right there. I can plug in my u. I'm going to get the integral of e to the u times du divided by 7. Now, hopefully, most of you know how to take this integral by now. But for those who don't, that's fine. You just need to practice on your own for a little bit, and you'll probably be fine. But this 7 in the denominator, I'm going to write out in front of my integral. Why? Because it's a coefficient. So now I have 1/7 e to the u du, just like this. I know this integral. Hopefully you do as well. And that's because the integral of e to the u is literally just e to the u. This is equal to 1/7 e to the u plus c. It's not my final answer, though, because I still need to plug in for u, which was 7x minus 1. So the final answer will be 1/7 e to the 7x minus 1 plus c. Final answer. Any questions?
So with the problems with the e that have something in the like exponent other than like other than x or u, you have to use U substitution because it's chain rule, right?
Exactly.
Okay.
Any other questions? Okay, now let's look at just another example real quick. This one will be slightly harder. Let's say I have the integral of 2x times e to the x squared power dx. So same idea. The first thing we're going to do is say u is equal to the exponent, which is x squared. By the way, if you choose e to the x squared, like if you choose e to the x squared as your u, this is wrong. This is going to get you a bunch of problems downstream. So it's just the exponent. It's just x squared. Then, again, we take the derivative. Du dx is equal to 2x. Again, we're going to solve for dx. So du equals 2x dx, and ultimately du divided by 2x is equal to dx. Same thing we've been doing all night. So now this is equal to the integral of 2x, because again, we don't touch the 2x, that's not what we're doing here, times e now to the u power, and then dx got replaced with du over 2x. Again, did I choose my right u for the U substitution? Yes, because the 2x's cancel here. Great. I'm left with the integral of e to the u du. And again, hopefully we know this integral. It's literally just e to the u plus c. But my final answer, still need to plug in for u. So final answer, e to the x squared power plus c. Final answer. Any questions on that one? Yeah, very fun. I love exponential integrals. I'm sure you're lukewarm to the concept, but the better you get at it, the more fun it will be, I promise. So next up, we're going to talk about integrals with the natural log ln. Okay, this is a very fun concept. So let's first deal with this problem right here. Number 1. If I have the integral of 1 over x dx, how would I solve this? There's two ways you could do this. The first way you can say is this. 1 over x. Can't I write this as x to the negative first power dx? In other words, you have an x to the first in the denominator. You can rewrite it as x to the negative first. Yes, this is technically legal. This is fine. The problem you're going to run into with this, though, is when we do the power rule. What's this integral power rule? Well, I would add 1 to the power. Negative 1 plus 1 is 0. So you'd get x to the 0. That's not a problem, actually, because x to the 0, that's actually just 1. The problem is when you divide by the exponent, which you do, you're going to get divided by 0. You can't divide by 0. This whole thing is wrong, which is funny. So instead, what you need to do is you need to recognize this as a red flag. Whenever you see 1 over x like this, or x to the negative first power, you need to recognize that this is a very straightforward integral. It's the integral is natural log of the absolute value of x plus c. That's the final answer. Now let me talk about where this comes from. So first of all, why is it natural log of x? Well, because think about derivatives, because you can always check your answer to any integral with the derivative. If I have the natural log of x and I ask you to take the derivative, hopefully you remember this, it's 1 over x. That's the original problem. That's the integral. So naturally, going reverse, it should be natural log of x. Now, where does this absolute value sign come from? That's a great question. I'm debating whether or not I even want to tell you because it's kind of a confusing definition, but maybe two of you will understand it and it'll justify me doing this. But let me first draw the function 1 over x. It's a function that looks like this. I'll draw it in red here. It has a vertical and horizontal asymptote at x equals 0 and y equals 0. This is the function y equals 1 over x in red. Now in blue, I'm going to draw the function for y equals the natural log of x. It's this function right here. Y equals natural log of x. Now here's the problem. 1 over x, my original function, that has a negative side to it. I can plug in -2, -3, -4, whatever, into 1 over x. I cannot plug in negative numbers into natural log of x. Because you can even try it. Plug in natural log of -2 in your calculator. Your calculator is going to yell back at you, error, because you cannot take the natural log of negative numbers. So that's why we say absolute value, because when we do that, now we include the negative values, and now we encompass the entire domain of the function. If that definition is confusing to you, luckily you never have to memorize the explanation. You just need to remember that whenever you see 1 over x, it's equal to natural log of the absolute value of x. Absolute value. The other thing you can imagine, just like for e to the x, if I have 1 divided by u, the integral of 1 over u du, like in other words, I did some u substitution that left me with a u in my denominator, just like this, then this integral is equal to the natural log of the absolute value of u plus c. And then the last step would be plugging in for u. Any questions? Okay. Let's look at some examples. Number 2. I have the integral of, let's say I have 1 over -3x plus 4 dx. This is a u substitution. Why? Because would be quotient rule if this were a derivative. But since it's an integral, it's a u substitution. Notice the Goldilocks method isn't very clear here what we choose. I'm just going to tell you, make your u -3x plus 4. Just make it the denominator. So du dx, the derivative, would be -3. And then again, I need to solve for dx. So du is equal to -3 dx. Divide both sides by -3. So we get du divided by -3 equals dx. Great. And now I'm going to plug in for everything here. I have the integral of 1 divided by, the denominator is just getting replaced with u. And then dx is getting replaced with du over -3. Now, this is something we've seen pretty much all day. This -3 in the denominator, what am I going to do with that? That's right, kids. I'm going to say it's a -1/3 out in front of my integral because it's a coefficient, and the 3's in the denominator. So the integral of 1 over u du, and again, this is the exact same thing we just saw a second ago. You say u to the -1st power du, and then you cross it out because you remember that's not what we do here, because you would get u to the 0 over 0 if you do power rule. Instead, this is -1/3 times the natural log of the absolute value of u plus c. And we're not done yet because we still have to plug in for u, which u we said was -3x plus 4. Final answer will be this: -1/3 times the natural log of the absolute value of -3x plus 4 plus c. And there we go. Any questions on that one? Okay, I have one more for you guys with natural logs. And by the way, this is my favorite integral out of any integral in the world. It's the integral of 1 over x natural log of x dx. This is my favorite one. It's actually really fun. So I'm debating whether or not I want to do the right u substitution or the wrong u substitution, because this one's not obvious. So I'm going to ask for a member from the audience to tell me what the u should be. And whatever you tell me, whether it's right or wrong, I'm going to do it. So I need a volunteer.
Is it ln of x?
Oh, okay. ln had her own TV show, which got canceled. This is the natural log. And yes, I make that stupid joke every time because my high school teacher made it. So naturally, I do too. I'm not going to tell you whether natural log of x is right or wrong. You guys are going to tell me because you know what we're looking for, if it's right or wrong. So then du dx, the derivative of natural log of x, is 1 over x. Now I need to solve for dx. There's a couple ways I can do it. I'm going to do it the hard way. The easy way is just cross multiply. X du equals dx times 1. This is easy because then you get dx right away. But let's say you miss this. I want to say what you do if you miss this. What you would do is what we've been doing all day. Du equals 1 over x dx. And now at this point, there's, again, an easy way and a hard way. The hard way is to divide by 1 over x on both sides. This gives you a complex fraction scenario like we talked about earlier, where you take the reciprocal, and I don't want to talk about that because it's confusing. The easier thing to do, to get dx by itself, multiply both sides by just x. The x's cancel here. The right side's good. The left side you have x du, and the right side you have dx. Regardless of whether you do the cross multiply method that I said from the get-go, or you did this kind of longer roundabout way of doing it, you're going to get the same answer. Dx equals x times du. Any questions with that? Okay. So now where are we? We have the integral of the numerator stays the same, 1. The x in the denominator we do not touch, but the natural log of x, that gets replaced with u. And we said dx just got replaced with x times du. So question, did the x's cancel? Yes, they do. This x is in the numerator, that x is in the denominator. Great. We have the integral of 1 over u du, which again, this is very straightforward. It's just the natural log of the absolute value of u plus c. Now, the last thing I'm going to say is we need to plug in for u. And we said u was the natural log of x. So does that mean the answer is the natural log of the absolute value of the natural log of x plus c? And the answer to that question is yes. And it looks silly, but this is my favorite integral in the world. And now I get to share it with all of you, which is the true gift of Thanksgiving. One more thing I want to mention real quick here. Notice the outer natural log gets the absolute value bars. The inner parentheses here, you can see these are parentheses. The inner ones are not absolute value signs. Does everyone see that? I'll take silence as a yes. Okay, great. That's it for that one. Any questions? Okay. Now we're going to move on to definite integrals. We can't forget about definite integrals because they will definitely be showing up. And they're not too bad. They're not too bad. And we've talked about them before together, or at least we did 2 weeks ago, which means you all forget for some reason, which is okay. So let's deal with this first problem here. I have the integral from -2 to 0 of x dx. Right away, you notice the big difference between definite and indefinite integrals. Definite integrals have bounds. Indefinite integrals do not. Luckily, the process stays exactly the same for most of it. In other words, if I ask you to take the integral of x dx, you should all know this integral because it's an easy power rule antiderivative. This is x to the first power, which means the integral is x squared over 2. I added 1 to the 1 plus 1 is 2, divide by 2, and then plus c, right? No plus c for definite integrals. Whenever you have bounds, instead I'm going to draw a long vertical bar like this. Up top 0, on the bottom -2. I'm actually going to be plugging in 0 and -2 in for x here and subtracting the two quantities. So what I get is 0 squared over 2 minus -2 squared over 2. So this is going to equal 0 minus -2 squared is now positive 4 divided by 2. I'm going to get a final answer of -2. Okay? Any questions? This is the answer. I have a question, and if you meet with me one-on-one, you can't answer this question. But anyone who doesn't, you are allowed. What does this answer -2 mean in the context of real life?
The area under the curve.
Correct. Great. Who said that? Just give me a first name.
I was Madeline.
Madeline. Tell me, did your professor tell you this?
No, I watched your last week's video this morning.
Great.
Or 2 weeks ago video.
I love to hear that I'm doing a better job than your professors. That always warms my heart. Okay. So, oh yeah, by the way, yes, I upload all of these to YouTube, And you can check out the ones from last week, as well as if you ever want to take physics for whatever reason, those videos are up there as well. Okay, so we're going to go from -2 to 0. These are the x bounds, by the way. And the area is the area in between the function, between the points x equals -2 and 0. This is literally what the integral means. The integral from -2 to 0 of x dx. Why is it this line, by the way? Well, because this is the line y equals x. That's the function. And what I'm saying is the black shaded area is equal to the integral from -2 to 0 of x dx, and that area just happens to be -2. So just to quick prove that this is right, well, this is just a triangle, right? And hopefully we all know the area of a triangle. Area equals 1/2 base times height. So the base, that's going to be 2. The height, that's going to be -2. The height is -2 because, well, that point right there is -2 comma -2 because the line's y equals x. So I have a height of -2. I have a length of 2. We're going to get an area of 1/2 times 2 times -2. That area is equal to -2, which is exactly what we got when we did using the integral. Any questions? Okay. So that's it for the first one. Obviously, you can't always use you can't always use area of geometric shapes. You can't always use triangles. You can't always use rectangles. Sometimes you need to do the definite integral, and let's look at some examples of that. Number 2, the integral from 1 to 4 of the quantity 2x minus 6x squared dx. Question. Well, I want you to think about this in your head. You don't have to call it out. Is this a U substitution problem? I'll give you a few seconds to think about it. Yes or no? Okay, time's up. Is this a product rule, chain rule, or quotient rule? The answer is no. As a matter of fact, if we wanted to, we could split this up into 2 integrals. Integral of 2x minus integral of 6x squared. Technically, you need dx here on both, and you need the bounds on both. So this is just going to be 2 power rules, just like we've seen all day. The integral of 2x is going to be, well, the 2 is a coefficient, times, this is x to the first. So I add 1 to the power of 1, like x, 1 plus 1. So I get x squared divided by 2. That's the left term. And then for the right term, minus, let's see, 6 times integral of x squared. That would be x to the 2 plus 1, which is 3, divided by 3. There we go. And then again, no plus c. Instead, I'm going to put this all in parentheses for notation purposes. And then a long vertical bar from 4 to 1. I now need to plug in 4 and then subtract when I plug in 1. Before I do that, remember when I said earlier about simplifying? Simplifying does, even though it's not necessary a lot of the time, simplifying is going to make your life a lot easier, especially for definite integrals. Why? Look at this. 2 cancels right here. 6 will cancel with the 3, leaving you with the 2 in the numerator there. In other words, this is easy. This is x squared minus 2x cubed evaluated from 4 to 1. That's actually how you read that, by the way. The long bar reads evaluated from 4 to 1. So now I'm going to plug in 4 first. So 4 squared minus 2 times 4 cubed. That'll be fun. And then that's it for the left one. Minus quantity 1 squared minus 2 times 1 cubed. That's not so bad. Close parenthesis. So this is going to equal 4 squared is 16 minus 2 times 4 cubed. As we all know, 4 cubed is 64. 64 times 2 is 128. And then minus quantity 1 squared is 1 minus 2 times 1 cubed is actually just 2. That's not bad at all. So 16 minus 128. Gosh, I hate mental subtraction. Negative 112. Yeah. Negative 112 minus negative 1, so really plus 1. We'll get a final answer of negative 111. Did I mess that up? I don't think I did. Okay. We'll assume I'm right, as always. Great. Okay, everyone ready for the next one? Any questions? Okay. Number 3. I have the integral from -4 to +4 of, in the numerator, e to the 2x Denominator, 2 plus e to the 2x dx. This is a very hard problem. Okay, so again, I'm going to call on a member of the audience. You can just call out. What will my u be for the u substitution? Not so easy, I know. Well, someone has to say... Go ahead.
2x. Is it 2x?
Okay, I'm not going to tell you whether you're right or wrong because, well, I'm not going to be there on test day. U equals 2x. Let's try it. Du dx, the derivative, is equal to 2, well, just 2. Then du equals 2 dx. And now I'm going to say du divided by 2 equals dx. Everyone good so far? Great. So this is equal to the integral from -4 to +4. In the numerator, I have e to the u. In the denominator, I now have 2 plus e to the u. And then dx just got replaced with du divided by 2. Notice, nothing canceled, but that's not a problem as long as... Do I have any x's here? No, I don't have any x's. So I'm good so far. But I do have one thing to say. Well, I mean, first I'll write this 2 out in front. So the 2 is a coefficient, 1/2 integral -4 to +4 of e to the u over 2 plus e to the u du. Now the next thing I want to say is, do we know this integral? So I'll tell you this, to whoever said u equals 2x, that's not wrong. Like that's one thing that I'm going to say it's an optional step, but we need to do one more thing. We are going to need another u substitution. Can I have another volunteer to tell me what the u substitution should be now? Okay, I'll just tell you guys. This is not easy, by the way. The u, which technically I can't use u anymore because I just used u, so I need a new variable. I'll call it v. V is equal to 2 plus e to the u. Now, I'm assuming at least one of you have a question. Where did v come from? Would anyone like to ask that question? You don't have to. If you understand it, then you don't have to ask. But does anyone have that question? Okay. Okay. I'm going to keep going. But I think this is going to get confusing because most people hate the double... it's called a double u substitution, but we ran out of u, so now it's called a v substitution. Whatever. But now the process is still the same. I'm going to find dv du, solve for du, so I can plug it in right there into du. That's the strategy. So what's the derivative of 2 plus e to the u? The derivative of 2 is 0. Derivative of e to the u is just e to the u. Great. Again, I'm solving for du, so I'm going to multiply both sides by du. I get dv equals e to the u du, and then divide by e to the u. dv divided by e to the u equals du. Is anyone confused yet? You should be. Oh, well. So
I have just like a question. Oh, sorry.
Go for
I
it.
just have like a question.
Yeah.
So like we didn't go over this in class. Do you think that this could show up on our quiz even if our professor like doesn't talk about it?
Yeah, so I want to say the answer is it's a possibility only because this problem right here showed up on your homework. Am I wrong? Not this exact problem, but like something similar to it?
I didn't finish the homework that's due tomorrow yet, so I'm not sure if it did.
Okay, I'll tell you. I saw a question just like this.
Okay.
And so for that reason, which by the way, if you want to, your original u can be 2 plus e to the 2x. That's actually like a lot easier, and it would get the job done. So in hindsight, they should have just not asked the audience for this one because this was hard. But hey, I'm trying to become the best of all time, which means right now I'm not yet the best of all time tutor, but we're getting there. Any other questions? Okay, I'm going to continue. And yes, this is confusing, but there's other problems where you need a double u substitution where you use v. So it's not a bad skill to have. Hopefully you never have to use it. You know what I mean? But it's good to know. I'm plugging in dv divided by e to the u for du. Let's see where we're at. 1/2 integral -4 to +4 of, in the numerator I have e to the u still. Denominator got replaced with v because I said v was equal to 2 plus e to the u. And then du just got replaced with du divided by e to the u. This is actually really good. the e to the u's cancel, and all we have left right now, I'm sorry, that's not du, that's dv. Yeah, this is very confusing, I know. So this is equal to 1/2 integral -4 to +4 of 1 over v dv. Hopefully you know this integral because it's the natural log. It's 1/2 natural log absolute value of v evaluated from 4 to -4. Now, real quick, we need to before we plug in here, before we do this problem, before we evaluate 4 and the -4, we do need to plug back in for u and then again for x, which is very annoying, I know. But it's going to be 1/2 natural log absolute value. V was equal to 2 plus e to the u. So 2 plus e to the u evaluated from 4 to -4. And again, I need to plug in for x as well. X was, we said 2x. So 1/2 natural log absolute value of 2 plus e to the 2x power, close absolute value sign, evaluated from 4 to -4. This is just a monster of a problem. And I'm probably not even going to, this is not going to be a pretty answer, I'll just tell you that right now. But we'll get a final answer of 1/2 natural log of the absolute value of 2 plus e to the, well, 2 times 4 is 8, so 8th power. We can't simplify that. And then minus 1/2 natural log absolute value of 2 plus e to the 2 times -4 is -8. This is about as simplified as we can get, actually, so I'm fine with this. Any questions on this one? This was just not a good problem, in my opinion. Okay, we're going to move on. We're going to move on to the next topic, which is area under a curve. So there is a difference between definite integrals and area under a curve. The biggest difference is the fact that a definite integral can be negative, while area under a curve should always be positive. So what does that mean? Let's just look at an example problem. Let's say I want to find the area under this curve right here. It's going to be this red shaded region right here. And the function is y equals x squared minus 4. Notice here, this area is clearly negative, right? But if I'm asking you to find area, then I want it to be positive. Area must be positive. That's just a rule of area. And yeah, that's pretty much it. So now in order to take this integral, the first thing I need to do is kind of find these x bounds. So notice this is actually not so bad. These x points right here are where the function touches the x-axis. In other words, I just need to set x squared minus 4, the function, equal to 0 and solve for x. Those will be my x bounds. So x is going to equal, well, x squared is going to equal positive 4, which means x is going to equal plus or minus 2. Because whenever you take the square root of both sides, it's really the plus or minus. So that is x.
I just have a quick question.
Yes.
Where did you get that 0 from? Are you just setting it equal to 0?
I'm just saying it equal to 0. Yep.
Oh, okay.
Good? Okay. So yeah.
Yeah, thank you.
The x points are -2 and +2. Which is good because now I have my bounds for my integral. So it's going to be the integral from -2 to +2. Notice my function is not going to be x squared minus 4 though. Why is that? Well, because if I do that, then I'm just going to get the negative area, right? Like if I choose x squared minus 4, whatever the area is, it's going to be negative. But I want it to be positive. So how do I account for that? Well, one way, this is like the cheat method, I can just put a negative sign out in front of that, and now I'm going to be good. There's a better answer, and I debate even showing you guys this, but the technical answer is you want to say the top function minus the bottom function, and the top function is the x-axis. It's the line y equals 0. So really, this should be the integral from -2 to +2 of the top function, which is 0, minus the bottom function, which is the quantity x squared minus 4 dx. Missed the dx up there. But you notice you're going to get the same result. So I recommend, if it's the x-axis we're talking about, just make it negative. And then
so when you say
yeah.
It's the x-axis that we're talking about, like, are you going to show us an example where it wouldn't be? Like, you mean if it's not the x-axis?
Yeah, so that's a great question. It's actually the last thing you learn about in the year. It's the hardest thing in all of calculus. And that is
wonderful.
If they ended on the easy stuff, they'd call it psych. I'm kidding. I've never taken a psych class, so I shouldn't have said that. But I love making fun of non-engineering majors because I'm an engineer. So, sorry. But let's just say, hypothetically, I have something like this. This is a weird shape. I see I have two intersection points here and here. And if I ask you to find this area in between this is absolutely horrendous. I will teach you how to do this at some point, probably next week. But for now, it's always going to be the x-axis, at least definitely for Friday. Any other questions? Okay. Also, just as a fun fact, do we have any psych majors here or anyone taking a psych class? No? Okay, great. I didn't offend anyone. Okay. So, where were we? Yes, I need to take this integral. I can either choose the top one here or the bottom one. It doesn't matter. But it's going to be, let's see. First, I can distribute the negative sign to both terms. So this is like the integral from -2 to +2 of -x squared plus 4 dx. I just need to take this integral. So the integral of this is going to be -x squared will become -x cubed divided by 3, because again, power rule, add 1. And then plus, what's the integral of 4? Well, that's just 4x. You just add x. I'm going to put parentheses around this, and then this is evaluated from +2 to -2. We should get a positive answer here. Let's see if we do. So -2 cubed over 3 plus 4 times 2 is just 8. That's the first when I plug in 2. Now subtract when I plug in -2. So -2 cubed over 3 plus 4 times -2, which will be -8. Let's see what we get here. I'm going to get -8/3 plus 8 minus quantity. -2 cubed is -8/3, but then the second negative makes it +8/3. And then plus 4 times -2 is -8. I'm going to combine this and distribute the negative. It's going to be -8/3 plus 8 minus another 8/3 plus 8. It almost looks like it cancels out perfectly symmetrically, except it doesn't cancel out. It adds on top of itself. It's unfortunate it doesn't cancel out to 0. But what this is going to be, it's going to be -16/3 plus 16. You can plug that in a calculator, whatever. This is the final answer as far as I'm concerned. And yes, this is a positive number, in case you're wondering.
So like on a quiz or exam, that would be like a question if it's asking us like what's the area under a curve for this function.
Yeah, that's the difference between a definite integral. A definite integral can be negative, and if they ask for area, then it's going to be positive.
Do you think they would just give us like the y function not already like in an integral?
I feel like I did that for this problem because, or are you saying because that's the example I did right here. Are you saying they would give an example not like this?
Yeah, like would they already give it with like
already with the integral sign?
And
yeah, so if they give it with the integral sign, it's no longer an area question. It's a definite integral question.
Okay.
And I'm trying to think of an example that would counter what I just said, but I can't think of one. Pretty much, there was some homework where, I mean, you pretty much did this, a lot of this. I would recommend looking back at that homework, whichever one that was. I wish I could tell you the number, but I just don't know.
With these kind of questions, like since we're only doing the ones with the x-axis right now, would we always put a negative sign in front of it?
Only if it's negative area. Like, look at this. This is clearly negative. If instead I chose like the positive area above the x-axis, now you don't put the negative.
But wouldn't that not be area under a curve?
You're right. So yeah, fair enough. So I guess I'm talking about this example right here, where it's the exact opposite. It's something like this.
Okay.
You know what I mean?
So because that's on top of the x-axis, it would not be negative.
You keep it positive.
Okay. Mm-hmm. Thank you.
Is anyone confused by that? Does that make sense to everyone? Okay. Now we're going to look at one more example. This one's really annoying, but that's okay. Let's say I have the following. This is number 2. We're having a great day today. At least I am. It sounds like sarcasm. I genuinely love what I do. That's why That's why I'm now only an engineer for 4 hours a day instead of 8, and that was a soul-crushing job if I've ever had one. But I love this. Plus, it's not psych, so let's be glad about that. So now, I have this area here in this region. You're going to see part of it's negative, part of it's positive. This, you can guess it. It's the function y equals the cube root of x. Now, for this one, we're going to need two different integrals. Why? Because part of it's negative, part of it's positive. So I'm going to say the area is equal to the integral from -1 to 0 of the negative cube root of x dx. Why would I say this? Well, because first of all, the function's cube root of x, and I'm saying negative cube root of x because that's the portion of the graph where it's negative. It's below the x-axis. So to make it positive, I just put a negative sign out in front of there. And again, notice the bounds. The bounds, I go from -1 to 0. I'm not going from -1 to 3 because the function's only negative in -1 to 0. Now I need to add a second integral plus the integral. This one's going to be 0 to 3 because this is where the function is positive. And this is going to be the positive cube root of x dx. And honestly, I should have seen this coming. I'm going to have to rewrite this as x to the 1/3. So x to the 1/3. That's also x to the 1/3.
Should we like know these parent functions?
In terms of what they look like on the graph? No, because you're not.
Because I have no idea.
Yeah, no. The answer is no because this is not for the AP Calc exam for high school. If this was the AP Calc exam for high school, then yes. Since this is not, no. But that's a good question.
So like they would give us y equals cubed root of x.
Yeah, that's right.
Okay. Thanks.
So where's the 0 and 3 coming from?
That one's coming. So does the left one make sense? -1 to 0.
Yeah.
So the right one's coming from the exact opposite reason. The red region in the positive is from x equals 0 to x equals 3. Do you see that?
Oh, yeah. I got it. Thanks.
Yep. Okay. So now we can take this integral. The integral of -x to the 1/3 power. So I'm going to add 1 to 1/3, which is 4/3. So -x to the 4/3 divided by 4/3. And yes, I'm going to rewrite that in the next step. This is evaluated from 0 to -1. And then plus x to the 4/3 divided by 4/3. That one's evaluated from 3 to 0. So now, finally, I'm actually gonna rewrite this. Again, this is why it's helpful to know your simplifications, because this would be kind of monstrous if I didn't know how to simplify this. But it's gonna be -3/4 x to the 4/3 power. Why? Because again, complex fraction in the denominator. I just rewrite it as the reciprocal as a normal fraction. Evaluated from 0 to -1 plus 3/4 x to the 4/3 power evaluated from 3 to 0. So now I can just plug in. I'm going to get -3/4 times, well, 0 to the 4/3 is just 0, minus a -3/4 times -1 raised to the 4/3 power. And then I need to add to that. I'm also going to go on to the second line because I ran out of room. Plus 3/4 x, which is really just 3 now, raised to the 4/3 power, minus when I plug in 0. So 3/4 times 0 to the 4/3 power, which again is just 0. This is kind of disgusting, but what we end up getting if you plug this in your calculator, you're going to get positive 3/4 for this whole thing. The first thing is just positive 3/4. The second thing would then be plus, oh my god, that's 3/4 times 3 to the 4/3 power, which you would just need to plug in and get a decimal. But this, as far as I'm concerned, is the final answer. Again, notice how both areas were positive. That's because area wants it both to be positive. If this was a definite integral, in other words, I don't care about the positive and negative and forcing half of it to be positive when it should be negative, our answer would be -3/4 plus 3/4 times 3 to the 4/3. But again, since I'm asking for area, that first region, we force it to be positive, so we put that extra negative in there to flip it. Any questions on that?
Do you have any idea if this is going to be on our quiz or if this is like just on the exam?
I'll be honest, I hope it's not in the quiz, but I want to tell you this. Based on pretty much what I've seen from this class so far, every time I think I nail it in terms of what's going to be on the quiz, they always give one example that I think was legitimately too hard and should not have been on it. So
Yeah, that's usually how it goes.
I'm hedging my bets and saying if this does show up on the test in any way, shape, or form, I'm a hero. And if it doesn't, then I'm a jerk. And I'm okay with it.
Because I know when we went over like the area under a curve, we
Yep.
didn't have a homework specifically on that. So he said it was more of just like understanding the concept of it.
Okay.
But like this is like actually doing it.
Yeah, I would say if I was a professor and I wanted to screw you guys over, which of course I would, then I would put a question like this on the quiz. But again, I never know for sure. I can only prepare you for the worst case scenario. So, if I were a betting man, I would guess no. But it's like 60-40. It's like barely in the favor of no. Any other questions? Okay, so the last topic we're going to talk about today is the fundamental theorem of calculus, which is actually one of my favorite concepts in all of calculus. Fundamental theorem of calculus. Now you may be wondering, why are we learning the fundamental theorem of calculus like this late in the year? Well, it's because, first of all, that's a great question. It pretty much comes down to the fact that in order to use the fundamental theorem of calculus, you need to know both derivatives and integrals, which is why we've only been able to talk about it at this point. So the fundamental theorem of calculus, I'm going to call it FTC for short, can be broken up into two parts. Part 1 says the following. If I take the derivative of an integral, of a definite integral specifically, like 0 to x, of some function f of t dt. If you're wondering why am I calling it f of t instead of f of x, it's a notation thing. If my bounds are the x, then I can't have x in the actual function. I need to choose a new letter, and most commonly in textbooks they choose t. So sure. So pretty much if I take the derivative of an integral, I'm going to get the original function f of t, except again I plug in x, which was the bound. I get the original function f of x. Is this confusing? A little bit, but here's the point. You see an integral sign, you see the derivative, then what's left is the original function. In the same way, if you multiply a number by 2 and you divide a number by 2, those two operations cancel out. This is exactly what we're seeing here for derivatives and integrals. Any questions? We're going to look at some example problems with this, so don't worry. Now, part 2 of the fundamental theorem of calculus, we've actually already talked about. So first I need to say the following. F of x, and this is a capital F of x, is equal to the integral of lowercase f of x dx. In other words, if I take the integral of f of x, I'm going to get capital F of x. Why? First of all, this is why does this matter? I'm going to tell you in a lot of ways it doesn't matter. This is just a notation thing. So what I'm saying is if I have the integral, this is part 2 of the fundamental theorem of calculus. If I have the integral from a to b of lowercase f of x dx, again, what's the integral of lowercase f of x? It's capital F of x. So let's just give a quick example just to show you. So if I have, let's say, x as my integral, the integral from 0 to 2 dx, we already saw this problem earlier today. I know this integral is x squared over 2. That's what capital F of x is. It's just saying whatever the antiderivative is, that's what capital F of x is. Now again, since this is a definite integral, I'm going to say evaluated from a to b, and then I'm going to finish up writing this by saying capital F of a minus f of b. You may be wondering, what on earth is this saying? I'm telling you, part 2, part 2 of the fundamental theorem of calculus is literally the definition of a definite integral. In other words, I took the integral of x squared over 2, evaluated from 2 to 0. I'm going to plug in 2 first, 2 squared over 2, minus 0 squared over 2. I get 2 as my final answer. This is what the fundamental theorem of calculus is saying, part 2 of the fundamental theorem of calculus. Again, what was part 1? Part 1 was derivative of an integral. What is part 2? Part 2 is the literal definition of a definite integral. If you want to write that down in some way that makes sense to you, go ahead. We're going to be focusing today on part 1 because that's the actual interesting part. part 2 we already did, and we already saw examples on it. So I'll give you another 10 seconds to write.
Is this supposed to be on our quiz, do you know?
I heard it was. I think it's 6.5.
Okay.
What did you say part 1 was called in?
Part 1 is when you take the derivative of an integral and you get the original function. Now, of course, it gets more complicated than that, and we'll look at some examples where that happens. But yeah.
Okay, thank you.
Mm-hmm. Any other questions before we get into the... By the way, this is the final topic of tonight. We're going to finish right around 9:30. I'm actually almost out of scrap paper too, which is kind of funny. I think this is 15 pages of scrap paper. I've only come to the end twice before in the now 1.5 years I've been doing this. So this was a very fun lesson. Okay. So let's say I have the following. Problem number 1. d dx, which means the derivative, of the integral from 2 to x of quantity 3t squared plus 1 dt, close parenthesis. Two things I want to mention real quick. In the above example, I said 0 to x. Does it matter that it's 2 to x now? No, it does not. No, it does not. It can be any number in the bottom position. As long as you have x in the top position and any number in the bottom position, we can do the fundamental theorem of calculus, part 1. Now, what does this equal? Again, it's just equal to the original function, 3t squared plus 1, except I'm just going to plug in x wherever I see a t. It's that easy. 3x squared plus 1, that's my final answer. It's so easy that it looks hard. If you know what you're doing, the fundamental theorem of calculus is very easy. If you don't know what you're doing, it's very hard. So now let's look at another example just to prove how easy it is. Number 2. I have the derivative of the integral from negative 10 to positive x of the square root of t, this is the numerator, the square root of t times e to the t divided by t cubed dt. Oh man, this looks tough. Well, good news. Literally all we're doing is, since it's the derivative of an integral, I'm just plugging in for x wherever I see t. The answer is square root of x times e to the x divided by x cubed. Final answer. Now you may be wondering, it can't be this easy, or else it wouldn't be calculus, it'd be psych. And you would be correct, because there is a couple caveats that make the fundamental theorem of calculus actually kind of difficult. Let's look at the first case. Number 3. The derivative of the integral from 0 to x squared of quantity t plus 1 cubed dt, close parenthesis. Some of you are saying uh-oh right now because we have x squared in the top bound. And you would be correct. You do have reason to be concerned. This is not super easy anymore. It's because we have to factor in the chain rule now. So the first thing stays the same. I'm going to plug in, this time, x squared wherever I see t. So this is equal to quantity x squared plus 1 quantity cubed. This is the first half. The second half is, because we have x squared as our bound, I need to multiply this by the chain rule. I've got good news and bad news. The bad news is this is not a fun chain rule. X squared plus 1 cubed, I mean, that itself is a chain rule. I've got good news, though. The chain rule I'm talking about is not this whole function. It's just the chain rule for x squared. What does that mean? The chain rule is going to be the derivative of x squared, which is just 2x. This is my final answer. Still pretty easy. Okay?
So anytime you have something at the top of the integral,
Yep.
the upper limit, that's not just x. Like if it was like x to the third,
Yep.
you would do the same thing times like 2x.
So what
3x
first thing I did
squared.
was the t got replaced with the x squared. It's not x plus 1 anymore. It's x, whatever the thing is. Do you see what I'm saying?
Yeah, so if it was like x to the third, you would do the chain rule with x to the third.
Yeah, then the only difference would be this would be x cubed, and instead of 2x, it would be 3x squared.
Okay.
And we'll look at one more example like this, so don't worry. Number 4. The derivative d dx of integral. This one's going to be new as well. On the bottom, I have 2x plus 1. On top, I have negative 1. This is of the quantity t minus 4 dt, close parenthesis. So now, not only do we have something different than just x in the bound, it's also in the lower bound. So question, do you think it matters that it's in the lower bound? For those of you who said yes, you would be correct. And that's because we can only use the fundamental theorem of calculus if it's in the top bound. If it's in the bottom bound, we give up. Thank you everyone for coming. It's been a great session. Okay, yeah, you're not falling for it. So what we're going to do instead is whenever it's in the bottom position, there's a property of integrals that says, hey, if I flip the bounds, like negative 1, 2x plus 1, I can flip the bounds. The only caveat is I need to write a negative sign out in front of the entire integral. So just as another quick example, if I had the integral from negative 2 to 0, I can rewrite that as negative integral from 0 to 2. If I flip, negative 2. If I flip the bounds, it means I'm flipping the entire thing. I'm taking the negative of the entire thing. Does this make sense? Any questions? Okay, so once we get to this position, now we're in the form we want to be in. And I'm just going to write a negative sign out in front because this negative is acting as a coefficient. So I'm going to replace t with what? I'm going to replace t with 2x plus 1. So negative quantity 2x plus 1 minus 4 stays the same. I can then put close parenthesis. And then I'm not done yet though, because remember, chain rule. Not the chain rule of 2x plus 1 minus 4, just the chain rule of 2x plus 1. The derivative of 2x plus 1, that is. The derivative of our upper bound. And the derivative of 2x plus 1 is just 2. And, I mean, this is actually not so bad. We can probably simplify it, but I'll just leave it like this. Okay? Any questions on that one? Nope. Okay, that's the fundamental theorem of calculus. And